Hi again. We are ready for the first track, and we have Alberto Barbati. Hi, Alberto. Good morning.
Hi, Marco.
Thanks for your participation to this conference. So I get off the stage immediately. Thanks for giving this session. So C++20 text formatting. Interesting. So let's see. And I get off the stage and I add your slides to the stream. Okay. See you later. Get off the stage and I add your slides to the stream.
Okay. So, hello and welcome to this C++ conference. Let's try this online. Okay. And I will talk about C++20 text formatting. Who am I? I am Alberto Barbati. I'm C++ programmer since quite some time, and I work in the video game industry. I'm currently trainer of game programming at the Digital Bros Game Academy. And I like to follow the works of the C++ community as an outsider, and not as a full member, of course. But since 2008, in 2008, I had published a little contribution to the standard. Let's start. What will we see today? We will talk about C++20, of course, which is introducing a new header, the format header. This header includes facilities for general purpose text formatting. These facilities are meant to be a replacement for printf and strings in a type-safe way, extensible, localization-friendly, and hopefully faster than the alternatives. The question arises every time we want to introduce something new that is a replacement of something that is already existing and that you are probably using since a lot of time. The question is, why? Of course, the answer is easy because it doesn't address everything that I written into the previous slide. Let's see what we have today in the standard and what are the issues that I'm talking about. Sprintf. Sprintf, of course, we all know Sprintf. It has been in the C library since the beginning of C. That is the beginning of times, maybe. It's a general purpose function and uses a string. This string here, the answer is %d, is a template that is used for formatting. The idea is that this %d is a placeholder, and the placeholder is replaced with the formatted value of the arguments here. So this function here, we all know that we'll write the answer is 42 inside this buffer here. I am mostly concerned with formatting to memory buffers, not with input-output, because that's the most common case in video games. Anyway, separating formatting from input-output is a good thing. In fact, one of the problems that we will see with IO streams is, in fact, that they try to get formatting and input-output in the same place, and that is a problem. The two problems are separated and should be treated as such. Sprintf here writes to this memory buffer. If the memory, as you can see, Sprintf only gets the start of the buffer. It doesn't get the size of the buffer, so there is a risk of overrunning the buffer if it has a fixed size. A safer version of Sprintf, which is called Sprintf-S, is available since quite some time, but I'm not sure every one of you is using that. Okay, the main issue with Sprintf and all the printf family functions are that it is type unsafe. We all know this. And why it's that? Because Sprintf is a C function, So all arguments are passed using the ellipsis, and so they are retrieved by the function using the VList macros and mechanism. This mechanism destroys the type of the arguments. So how does printf know about the type of the arguments? They are passed in the placeholder. Let's see the placeholder here, person D. D requires 42 to be an integer. And we all know that bad things may happen if the type implied by the placeholder doesn't match the type of the argument. Yes, it's true that more recent compilers mitigate these problems with static analysis. They can actually compare the placeholders contained in the template string with the arguments and provide a compile time check in form of warnings that you can see. So this problem is actually mitigated, but doesn't work every time, because if the template string is computed at runtime or read from a file, then this kind of compile time check cannot happen. One other thing that is missing is support for user-defined types. The list of placeholders is completely specified in the C standard, so we can't have any type that is not contained in the C standard. So we have integers, floating points, strings, and that's it. You don't have any other type. Another issue, I'm quite concerned with locale. You will see that we'll talk about locale often in this talk. Number formatting is always locale dependent with printf. Not only that, it relies on global state, because all C library function relies on the set global function, set local function that is global for the entire application. This can be a problem if you need both C-locale, C-locale is unlocalized formatting, and user locale formatting in the same program. Why would you need both locale in the same form, in the same program? Well, imagine that you want to present data to the user. In this case, you would like to use the user formatting, user localized formatting, but at the same time, your application needs to write the same data to some JSON file, for example. We all know that JSON files want all numbers to be formatted in the C locale. If you ever try to format numbers in a different locale and put it into the JSON format, that you will have bad results when you pass them back. I've been there and it's not funny. And since we are accessing global states, if your program uses multi-threading, that you are in deep trouble, because you also have race condition if you switch the locale on a thread while another thread is using it. Argument matching. If a template string includes multiple placeholder like this, %s and %d, we all know that the first placeholder is matched with the first argument, and the second placeholder is matched with the second argument. Okay, that's not a problem. We all know that, but I don't know how many of you had the problems with localizing an application. This today is June 13, is good in English, but if I would need to write it into Italian, I will need to write oggi è il 13 giugno, and 13 comes before June, with giugno, which is June. So not only I have to change the template string, I have to put the %d before the %s, but I also need to exchange the two arguments. Is it a problem? Yes, it is, because you can't localize this application easily without by only using a data-driven approach. In a data-driven approach, you typically only translate this sentence. So you read the template string from a file, and you keep all the code intact. You can't do this because if I use this template here and I do not swap these two arguments, then bad thing will happen because day of month is a number while month is a string. So that iostreams are the C++ replacement for printf. Of course, we all know that it didn't actually replace printf. iostreams are well known. They are in C++ library since the beginning of C++. They are general purpose. They took a completely different approach. Instead of using a template string and with placeholder, they just use chains of this insertion operator like this. And all the Hello World applications use this syntax, so it's quite common. Are iostreams better than printf? Well, a little. For example, we get type safety. The correct format function is selected at compile time. It is inferred from the argument type. How does it happen? Because simply because of the function overloads resolution. The insertion operator is overloaded for all different types, and the correct one is selected at compile time. It's also extensible because it's easy to write formatters for user-defined types. All you have to do is to provide another overload for the insertion operator. And I'm pretty sure that several of you already did this in your programmer life. Are there other advantages? Well, no. There are other disadvantages. For example, since we have no placeholder, the problem with localizing this kind of formatting is even worse than with printf, because there are two different strings here, and we would need to localize both this and this, which is a space, which is quite stupid to localize. But even in this case, we would need to change the code to swap these two arguments here. Not only, the code is often verbose and difficult to read because, for example, in this case, it's easy to miss this blank here, and it's verbose to have these 1, 2, 3, 4, 5, 6, 7 characters only to insert a space. Other issues, even iostreams have issues with locale, because number formatting is always locale dependent, even with iostreams. It's a bit better than with printf because we are not going to access global state each time, but we have a per stream locale object. So each stream has its own locale object. The default value, which is the locale global, which is determined when you construct the stream. But after construction, each stream has its own. You can change it with the InView function. And as long as you do not share streams between multiple threads, you don't have data races if you change the stream on one stream. Okay, you can have both clocale and user locale formatting with iostreams. The best course of action is to have two different streams. So I have one stream with the user locale and one with the clocale, and that would be easy. But you can also juggle with InView with the InView function to change the locale during the on the stream while formatting. One thing that has to be noticed, that there's an overhead cost even if you use the clocale. That is because of how the design of the locale and iostreams is. And as we talking about this, the iostreams implementation are not known for good performances. even if you don't use, even using the silocale. They are known for increasing the code size and also to add some memory consumption. The design, as I said, doesn't allow much improvement. It relies heavily on polymorphism, virtual polymorphism, to handle formatting, locale, buffering all at the same time. And if you only need formatting and you don't need locale, you are paying for all this. And we were talking about memory buffers. If you want to format in memory, then IOStreams mandate you to use std string. That may not be such a big deal, but if you already have a preallocated buffer, this means that you have to format to a string, which may require dynamic allocation, and then also copy to your buffer. So the design mandates this this complication, and so it may be inefficient. Okay, so what do we have? Of course, we can decide not to use the standard, not to use printf, not to use IOStreams, and use other formatting libraries. These are a list of available formatting libraries. Of course, it's not exhaustive. I'm pretty sure most of you have used at least one of these, and at least the same amount have used something that is not listed here. I also did a small informal survey some time ago, and several projects are actually using printf, but they are wrapping it into some higher level function which match the framework in which they are using. But there is one formatting library that is not listed here, and I want to talk about this, and it is called FMT. FMT is quite a recent library. The FMT, the first commit on GitHub on the FMT library is from 2012, but actually it took some time to get up to speed and to get to the form that we have today. What it is. I'm talking about this because it is the reference library that led to the format proposal. FMT is an open source library maintained by Victor Verovich. Hi, Victor, if you are listening. And it is available at this address here. It is distributed under the MIT license. It's portable. You can compile it with GCC, Clang, and MSVC. It also have quite affordable requirements. The latest version requires itCppCppCon20, but that's also an old branch that is still maintained that may work with itCppCppCon98. Of course, with not with all the functionalities. The FMT library has been proposed for the first time in mid-2017, and after a few iterations has become the format library. Just to give you a glimpse, one of the goals of the FMT library was speed. This benchmark is taken directly from the FMT library GitHub repository. As you can see, FMT libraries compares, this is a benchmark about floating point formatting, and it is definitely faster than both StringStream, StreamStream, which are deprecated, and also sprintf by a large amount. This double conv here is another library that was taken as a reference. So FMT become formats in C++20. Of course, not all of this, only a subset of FMT has been included. According to the Victor Zverovich, this has been done in order to simplify the adoption from the C++ committee. But do not worry, the subset that has been included in C++20 is more than enough for everyday use, and we will see about that. And who knows, a few extra FMT features might also be considered for C++23. So how does a format function looks like? It looks like this. It's function. We are back to the idea of having a template string with placeholder. The placeholder is this one with the braces, and without much fantasy, 42 will be replaced in here where is the placeholder. If you are if you know Python and other languages, this syntax here is clearly inspired from those languages, from Python in particular. And what is the advantage of this? Format is a C++ function, not a C function. So the arguments here are passed as a variadic templates. So formats, the function knows about the types of its argument, not as we saw it would happen with printf, which is a C function. So we get type safety. We see that the placeholder here has no information at all about the type. With the same placeholder, we can format whatever, an integer, an unsigned long, a floating point number, a string, whatever. The type of the argument is taken into account, and the format function is able to do the correct thing and put it where in place of the placeholder. Argument matching. We talked about argument matching before with the printf function. Of course, if I use the placeholder here, matching would be positional. It wouldn't make sense to do otherwise. So the first argument replaces the first placeholder, the second placeholder, the third placeholder. But we have good news. We can override automatic indexing by specifying the actual index. If I use the index here, then this placeholder will not take the first argument, but rather use the index. So 0 is the first argument, 1 is the second argument. But if I swap the two indices, then this is the second argument and this is the first argument. Oh, now I can translate today is June 13 to oggi è il 13 giugno only by changing the format string. And this is very easy to localize in different languages your application, because you just need a table of these strings here, and you don't need to worry about the order of the arguments. One thing that we can do, we can also omit some indices. In this case, the second argument is ignored because there's no placeholder that mentioned 1. And we can also repeat the argument multiple times. One thing that we cannot do, we cannot mix automatic indexing and manual indexing, either or automatic indexing or manual indexing. If you try to format this, you will get a format error exception at runtime. Okay, what type are supported by the library? There are a lot of them. Of course, all the basic one, all the arithmetic types, integer, floating point, boolean, char, and white char. The char 8, char 16, and char 13 types are at the moment excluded, because these types actually work on a code unit base rather than on a character base. So it's better to leave them off until we understand how to deal with those. Of course, we can format string type, both new terminated strings, passing a const pointer, but also char arrays, third string, and string view. We can also format pointer types, but only void pointer and null pointer. Of course, formatting null pointer is quite easy. It's real. And if you want to format a pointer of a different type, remember to cast it to void pointer, because since the format function is a variadic template, there will not be any implicit conversion to void star. One thing that we get out of the box in C++20, that we can format a few types defined in Chrono, most of the useful one, of course. So you will not need to use special format function like strf time to format date and type, the time and date types defined in Chrono. You can just put it into format and they work. Okay, format specifiers. Sometimes it's not one value can be formatted in multiple ways. Sorry. For example, an integer may be formatted in decimal format or in hexadecimal format. For floating point numbers, we may want to specify the number of significant digits. How do we do with this syntax? So we do it like this. We have a space for specifiers that I will going to describe in a few slides. The specifiers are always introduced by this column. The column has to be present even if the index is missing, and especially if the index is present, to separate it from the index. How does the specifier look like? The interpretation of the format specifier is determined by the type of the matching argument. This is important. We said that the matching type, the type of the argument has to be taken into account. So it's the type that dictates how the format specifier is interpreted. If a type doesn't support a specific format specifier, you will get an exception, a format error exception. If you are worried about these exceptions at runtime, I have a little good news for you. The library design is open to the possibility to have the format string parsed and checked at compile time. However, unfortunately, C++20 still lacks the language support to have the check be performed automatically. FMT, the FMT libraries actually implements compile time checks, but requires an explicit opt-in. You have to put a little tag on the format string for compile time checks to happen. We'll see about in C++23 if we can, if we will be able to have compile time checks automatically. However, I'm confident that somehow implementation would implement some ways, like static analysis, like the one that we are able to use with sprintf, to have some kind of checks of the format string before C++23. Okay, let's have a look at this format specifier. For the common types supported by the library, the format specifier has this form here. Oh, a lot of stuff, but do not worry, every single piece is optional, so even a completely empty format specifier is good. A few pieces make sense only for specific types, so if you use for the wrong types, you will get an exception. You can refer to this page here in the standard for details about all the format specifier. But if you are lazy, you can have a look at the documentation of the FNT library. It's all written there. The standard specification are written in terms of this, so it's quite adherent to the standard here. Okay, common specifier. There are a piece, some common piece that I will that work as they do in sprintf. Sprintf has equivalents for all this. so we get over this quickly. Sign controls the presence of the plus sign before positive numbers. Sometimes you may want plus signs, positive numbers to have a plus sign. Sometimes you do not want it. The hash switches to alternate formatting, which means can mean different things according to the types. For example, for integer numbers, we will see in a few slides, we'll introduce the base specifier. 0 is specifically for integers and introduces 0 padding. And width and precision works exactly like they do in printf. The width specifies the minimum output width, and precision specifies the maximum output width for strings, or controls the number of digits for floating point numbers. Okay, so all of these have a similar equivalent in printf, so there's nothing new. Let's have a look at something that is new in formats. Suppose that we specify a width, an explicit width, which is a minimum output width. What can we do with format is that we can control alignment. These are, for example, examples of outputs with a fixed width of 8 characters. And we can see that I can align the output on the right, on the left, or even in the center of the allowed space. We can specify a filler character here. This is the filler character. If we don't specify the filler character, as we do here, then the library just uses a blank space. Please notice that the default alignment is the right for numbers and is left for the strings. This is also consistent with what is done with printf. And locale. We talked about locale already a few times. How does the format function works with locale? Locale is opt-in. So if we don't require explicitly with this uppercase L specifier, then formatting will always use the clocale. So in this case, whatever locale I'm in, for example, if I am in the Italian locale, this will produce the output with the decimal point, the period. However, if I request the localized formatting with the L format specifier, then I will get a comma as a decimal separator. And this is good because in this case, we don't need to access the locale at all. And that's why formats behave so well with respect to printf, because the code may use an optimized path that bypasses completely the locale formatting and uses directly a function that is optimized to produce this. The locale, where do we get the locale? We can either use the global locale if we don't care about race conditions and we are fine with using the global locale, or we can just pass the locale as an argument to the format function. We will see in a few slides. Please remember, if you want to use the FMT library, please use the latest one, because before the version 6.2.1, which is the most recent one, the library used n, the lowercase n, instead of the uppercase L. This is from this version onwards, the uppercase L is used to ease migration between the format library and the future itCppCon20 format library. Okay, so let's see some formatting example using, for example, for integers as a few format specifier. D that produces decimal output, B produces a binary output, O produces octal output, and X, of course, produces hexadecimal output. We can also have use the uppercase X to have the uppercase A if you want. The hash symbol here, we said that switches to the alternate format that it's introducing this base specifier here, this 0x here. Of course, it works also for octal and binary. It uses 0 here and 0b here. And here, how does the zero padding work? If you put a 0 here, then we zero pad the number up to the specified width. And this is friendly with the base specifier. The zero padding occurs after the base specifier and not before. Let's see some floating point formatting example. Okay, one good thing is that unless you require localized formatting, floating point formatting rely on the C++17 function toChars. If you don't know about this, I will encourage you to have a look because they are pretty nice function that are very that provide the most performant way to format floating point numbers. And the specifier for floating point numbers are F, Z, E, and A that directly match with the Kers format equivalent. The default one is the overload of toChars that doesn't get a char format that produces this. And if you wonder why these two are different, then the answer is easy, because the default implementation of toChars produces what has a nice property. It is the shortest representation that guarantees round-trip parsing. So if I format this with the default format specifier, then I will get something that if I pass it back, I will get exactly the same result. This is not something that you can easily get with printf, because printf will probably write something like this. And you see that we are missing a few decimals. And this is really a nice property if you want to format, for example, in the case that I mentioned before, if you want to write something in a JSON file and you want to pass it back and have the same data that you put into the file. Okay, so let's see the formatting function that are provided by format. The simplest one, I already introduced this, is format, is a variety template. It takes the template string with a string view, so you can easily pass strings, literal strings, string view, and also strings they come from strings as third string, and take the arguments here, and it returns a string. For example, you can just get a string or format a string and put it on cout. Actually, we have 4 overloads of formats, the one that I just mentioned, and other 3 versions.
Alberto.
One that takes explicit locale. So
Alberto,
this one
can you hear me?
takes if localized formatting is requested, then it takes locale from the global state, and this takes it from this object here. And we also have versions for the white strings.
Alberto, can you hear me?
And all the function that we will see here have all these 4 overloads. Okay, you can directly format into a container if you don't want to allocate a string. This format 2 here takes an output iterator. And nothing that this version doesn't output the null termination. So it puts only the formatted character into the output iterator. How do you use this function? For example, you can use a back inserter iterator to populate a vector without previously allocating the buffer. Or you can use a stream buff iterator to directly format to cout without allocating a temporary string. And of course, we can format to a fixed buffer. We don't want to have the problem to run the risk of overriding the buffer. So there is a version that takes the output iterator as before, but also the maximum number of characters. In this case, no more than n characters will be written to the output iterator. So to avoid over buffer overrun. This format to n result type here, it's quite funny.
I think we have a problem.
Fancy, actually. It's just a structure that has two members. The output iterator as the format2 function, but also the size, which always will be the full size of the formatted string. Not the number of characters that are put into the output iterator, but the number of formatted characters that would go in the output if we add enough space. Let's see an example of this. For example, if I have a buffer that is big enough, we have a buffer of 20 characters, and I want to format the answer is 42. What do we get here? We will get the answer is 42. The rest of the characters are left uninitialized because they were not initialized here. They are left untouched by format2n. The out iterator is would be the pointer to the first character after the formatted one. So it's here, which is buffer plus 16, because these are 16 characters. And size, of course, is 16, because the string, the formatted string is 16 characters long. If I add a smaller buffer, the same example, but with only 10 characters, then only the first 10 characters will be written without the null termination, of course. These are exactly 10. The output iterator, of course, is the points to the past the last formatted character, so it would be here. But size will always be 16, so that we know that the buffer wasn't big enough, and we know the actual size. So if we want to provide a larger buffer, we can we know exactly the size. Actually, if we want to know the size of the formatted string without having a buffer, we can just use the formatted size function. This only computes the size of the formatted function or the formatted string without without any output. Okay, you maybe wonder, since we talk about code size, do all these variety templates produce code bloat? Actually, no. The library actively fights code bloat by using this approach.
Alberto, last attempt. Can you hear me?
The function that we saw are actually
no, I think he can,
thin
inline
wrappers
actually.
That call this
folks,
make
I have
format
to,
args
I have to close this stream. I'm really sorry.
All the argument into a type
I have
array
to switch
structure,
to the next
and
session with
then they
Ivan
call this
Vucic,
type array
and
structure
you
in
can anyway
this
follow up
function.
this.
This is a function, not
You can anyway follow up this with Alberto on Discord. You know, technical issues can happen. He cannot hear me anymore. So anyway, please give feedback about this session, and I'll drop you here the link. So see you in the other video with Ivan Vucic and Lighting Talks in the track B. I'll follow up Alberto in another way. I hope he will reply. Cheers.